All right, what I have done here is over on the left side of this, or sorry, the right side of the screen, I've drawn us a free body diagram. There's really only two forces that are acting on the pendulum. There is a gravitational force called W, and there is a tension force in the string that points along the direction of the string. Those are the only forces that are going to be acting on this object. And then I'm going to go ahead and use the Newton's second law for rotation for this object, choosing the place where the string is attached to the ceiling as my origin. That's going to give me a net torque, which is only due to the gravitational force and happens to be negative in this case. It's pointing into the board because I've pulled the mass up to the right. So it's going to be equal to the weight, gravitational force, which is m times g, times the length of the string, which is the radius vector, times the sine of the angle in between those two things, which here happens to be the angle theta that you can see on the screen. And then I have set that equal to I times alpha. I was given as ml squared, and I'm off to the races here. So I do some quick canceling. You'll see that the mass actually cancels out here. We've seen that happen in a lot of physics problems. And I have an equation which says that alpha is equal to minus g over L sine of theta. And just like we did in the block on the spring case, I can write alpha, the angular acceleration, as the second derivative of theta, which is the angular position.